Good morning or good afternoon. These are pretty much lecture notes for friction forces and dealing with the different types of friction for AP Physics 1. So, quick review. We've already introduced friction and we said that it has to do with the fact that at the microscopic level you have these bumps and ridges and troughs, as well as some intermolecular forces, so forces between molecules, that cause a resistance to sliding. And we actually split those resistances into two main categories. We had a static case, where we have the friction that acts while stationary, and we had the kinetic case, where the friction acts during motion. So let's go on and review what is different about these two. So kinetic friction, of course, is our sliding friction. And every single friction we have depends on really two things. It depends on the materials that are in contact with each other, and it depends on the force that is pressing the two surfaces together. So we see that in both of these equations for the kinetic and the static friction. So what is the difference between the two? Well, firstly, kinetic friction tends to be smaller than static friction. So most of the time, our kinetic friction is going to be smaller than our static friction for any particular pair of objects and any particular normal force. So the only difference really is my object moving or is it stationary? So if it's moving, all I need to do is know the normal force and the coefficient of kinetic friction to calculate a kinetic friction force. For static friction, it's a little more complicated because if you see in this, our static friction is actually only calculated as a maximum static friction. So this is the maximum force that friction can provide to resist moving. So let's see how that works. Well, if I am looking at static friction, I'm looking at an object that is stationary. So here is my object. It is stationary. I'm going to apply some force to this object, and friction is going to resist. So if I'm talking about static friction, we'll say that there is this friction force going this way, static friction force, and as I apply more and more force, my static friction force will increase in order to combat my applied force. But at some point, right here, we are actually at our maximum value. So it's our maximum static friction. And that is where mu s times n tells me my static friction. Before that, it's whatever is required to keep me stationary. Beyond this, you see that we actually have the force of friction dropping off. So here is my kinetic friction region. And as soon as I start moving, it now requires less force to keep me going, essentially, because my kinetic friction is smaller than my static friction. So you can kind of see, looking through all of these example coefficients of friction, that coefficient of friction tends to be between 0 and 1 for most cases. There is some situations where rubber is a little bit more sticky, so to speak. So rubber is a pretty good friction force, if that makes any sense. This is why we use it on tires. So going on, let's actually take a look at static and kinetic friction in a situation here. So I have this box. It is a 10 kilogram box. I'm going to go ahead and draw a free body for it. I'm going to draw it up here on the right. So I have mg acting downward. Draw that a little better. I have a normal force acting upward. I have an applied force to the right, and I have a friction force to the left. So I'm given that mu of static friction is actually 0.4, and the mu for kinetic friction is 0.3. So here are my two mu's. Now, when I go back and look at this problem, I'm looking for the force of friction depending on the force that I am exerting on it. So I'm going to go ahead and calculate my static friction force and my kinetic friction force. So my kinetic friction and my static friction are both dependent on mu and normal force. So this is my maximum static friction force is going to be mu s times n. And so for me, that's going to be 0.4 times my normal force. Oh, I don't have my normal force. Well, let's go over here real quick. In the y direction, I have a normal force acting upward. I have mg acting downward. And this is in the y direction. And there is no acceleration in the y direction. My box is not lifting up off of the ground. So my normal force in this case is just equal to mg. So my normal force is actually 10 times, we're going to use 9.8 here because it becomes significant for this example problem. So my normal force is 98 newtons. So now I have 0.4 times 98. And so my static friction max, my Fs max, is going to be 39.2 newtons. Now my kinetic friction force is going to be mu k times normal force. So here I have 0.3 times my 98. So my kinetic friction force, and this is not Fk max, it is just Fk, is 29.4 newtons. So let's go through these. So for the case of A, my applied force is less than the maximum static friction. So because that is the case, so Fa is less than Fs maximum. Because of this, that means my object's not going to move. So I'm actually going to see that in any situation where I have not applied enough force to get it to move, I am going to be stationary. So if I apply 0 newtons of force, the friction force is just going to be 0 because of this situation right here, where in the x direction, my applied force minus my friction force is equal to ma. So if I'm not moving, it's equal to 0, and my applied force is equal to my friction force. So for the case of A, where I only apply 0 newtons, then my friction force is 0. When I apply 10 newtons, my friction force is 10 newtons. When I apply 20 newtons, my friction force is 20 newtons. When I apply just barely underneath the static friction force, then I am still not moving. So I am applying 38, and I'm getting 38 newtons back in friction force, resisting my motion. So as soon as I go beyond my maximum friction force, I know that I'm going to start moving. So all of a sudden, what is happening? I'm using kinetic friction. So now my force of friction is equal to that of my kinetic friction. So because I'm moving in E, my frictional force is my kinetic friction. So now let's move on and take a look at a situation where we're actually kind of calculating things. So for this one, we're going to calculate the coefficients of friction. So I have a 500 Newton crate. So remember when I describe something as a 500 Newton something, then I am talking about the weight. So this right here, my weight is 500 Newtons. So when I draw my free body, I'm going to label it like that. To start the crate moving, I have to pull with a 230 Newton horizontal force. All right, so let's see. We have a normal force here, and then we have some pulling force, and this whole thing is about friction, so we're going to assume that there is some kind of frictional force this way. So to start it moving, I have to apply 230 Newton force. So what does that tell me? Well, that tells me that my 230 Newton force is going to be equal to my static friction maximum. So I can actually say that my static friction maximum is going to be equal to mu s times my normal force. So my mu that I'm looking for here is my static friction maximum over the normal force. So substituting here, I'm just going to have 230 over my, I need to get my normal force. So how do I get normal? Well, the sum of forces in the y direction is going to be normal force minus weight is equal to ma in the y. And I am not accelerating in the y direction, right? I am not lifting up off the ground. So my normal force is equal to my weight, which is 500 newtons. So I go back and I'm dividing 230 by 500, and you see that this just works out to be 0.46. So one of the things that's important to point out here is that my coefficient of friction actually does not have a unit, right? This is a Newton, and those newtons cancel out. So static friction coefficient has no units whatsoever. So now let's do the same thing for the coefficient of kinetic friction. So once it starts to move, I can keep it moving with a constant velocity of 200 newtons. So here I'm thinking, all right, F of x, so sum of forces in the x direction, is going to be my pulling force minus my kinetic friction force is equal to ma x. And they just told me that this acceleration is 0 because I'm moving at a constant velocity. So my pulling force is equal to my kinetic friction, which is in this case equal to 200 newtons. So kinetic friction is going to be equal to mu k times my normal force, or mu k is equal to my kinetic friction force divided by my normal force. So now I just substitute 200 newtons divided by my 500 newton normal force is going to give me a coefficient of kinetic friction of 0.40. So here are my answers: 0.40, 0.46, and this is actually not very difficult to figure out coefficients of kinetic friction. All right, so moving on to another example, we have the same box, but in this case, I'm actually pulling it at an angle. So let's draw a free body diagram for this. So the free body diagram for my box is going to have the weight of the box, which is still 500 newtons. It's going to have a normal force acting upward, and now it has some kind of pulling force at an angle. And this angle is 30 degrees. And then I have a friction force acting to the left. And so in this case, I'm trying to move with constant velocity. So I can go ahead and label this as kinetic friction. So the difference here is that I have a force at an angle. So let's go ahead and actually just apply Newton's second law to this free body diagram. So I'm going to start in the x direction, and I see that I have a component of my pulling force that is in this direction. So this is F pull in the x, and I also have a component in the y direction, right? So this is F pull in the y. And so for my sum of forces in the x direction, I would want F pull times the cosine of 30 degrees, is the positive way, minus the frictional force. And this is equal to ma in the x direction. Well, my x acceleration is 0 because my velocity is constant, so this is 0. And I'm actually going to go ahead and replace my kinetic friction with mu k times n. So my F pull times cosine of 30 degrees minus mu k times normal is equal to 0. All right, so I'm looking for force pull. So I'm actually going to go ahead and solve this for force pull. So add mu kn to the other side and divide by cosine of 30. So I have mu k times normal over the cosine of 30 degrees. So I have mu k, it's given to be 0.4, and I don't quite have my normal force. So let's look at normal force. So for the y direction, I have the following forces. I have a normal force acting up. I also have the y component of the pulling force. So that's Fp times the sine of 30 degrees. And then I have the weight acting downwards. And this is equal to ma in the y. Well, I am still moving constant velocity. I'm not accelerating in the y direction, so my y acceleration is 0. So my normal force is actually going to be my weight minus Fp sine 30. So my normal force, I'm going to go ahead and actually solve for this if I can, which I can't because I don't actually have Fp. So I'm actually going to go ahead and substitute that in here. So I have a weird situation. So I have Fp is equal to mu k times W minus FP sine 30 degrees all over the cosine of 30 degrees. Okay, so now we need to do some simplification. Oh boy. So I'm going to go ahead and actually move the, I'll leave the cosine 30 there. So we have force pull is equal to mu k over cosine 30 times W minus mu k over cosine 30 times FP sine 30. Ooh, this is messy, but we can make a little simplification. So one thing we can do is we can say that, I'm going to zoom in, we can say that the sine of 30 over the cosine of 30 is equal to the tangent of 30. So this is a simplification we want to make. So what that allows us to do is it allows us to take this, and it is ugly, and what we now have is FP is equal to mu k over cosine 30. I'm actually going to start substituting so we can get rid of some of these variables. So mu k is 0.4, cosine 30 is, well, it's 0.866, so maybe I'll leave it as cosine 30 for right now, times the weight, which is 500, minus, now we have 0.4 over, oh, actually nothing. So we have 0.4 times FP times the tangent of 30 degrees. Okay, so now what we have to do is we have to add, and sorry if it skipped around, the recorder crashed. So I am now adding this to the other side. So I have FP plus 0.4 tangent 30 FP, which is, and so this is actually, we'll say 0.231 times FP. And that's equal to, we're going to go ahead and evaluate this, which is, caught me doing math, so this is 230.9. So now I just add that together, so I divide by 1.231, and I find that my pulling friction force is about 187 or 188 newtons. So this is a rather long problem, but what we see is it's essentially applying Newton's second law and solving a slightly more complicated system of equations. Okay, now we're moving on to a situation where there is some acceleration. So what's going on? Well, let's redraw our free body diagram just so we are 100% sure. So here is my box. I have mg acting downward. I have a normal force acting upward. I have a pulling force, again acting at 30 degrees. And then I have a force of friction in this direction. So I know that it's going to be kinetic friction, and at this point, it's okay to write that my F is actually equal to mu k n. So I can just write that into my free body diagram. So I know that my kinetic friction coefficient is 0.3, so I'm going to jot that down. And I know that pulling force is equal to 40 newtons. And then my mg is going to actually be 10 times, we'll use, let's go ahead and use 10. So my mg is 100 newtons. So let's calculate the acceleration. Well, all we're going to do is we're going to do sum of forces in the x and sum of forces in the y. So in the x direction, just like the last problem, I have force pull cosine 30 degrees minus mu k times normal force equals ma in the x direction. Now, in this case, my acceleration is not 0, so I have to leave this as it is. I'm going to go ahead and jump to the y for a minute. In the y direction, I have normal force plus Fp sine 30 degrees minus, well, let's just do 100, equals MAY. Now, even though I'm accelerating, I am accelerating along the horizontal direction. So my acceleration is actually this way. So my y acceleration is still 0. So this helps quite a bit because now we have normal force is equal to 100 minus F pull sine 30. So let's go ahead and make this simpler. So normal force is 100 minus, so my pulling force is 40, so that's 40 times the sine of 30 degrees. And the sine of 30 degrees is 1/2, so this is actually just a normal force of 80 newtons. So plugging that back in to my blue equation here, I actually have my pulling force, so 40 cosine of 30 degrees, minus 0.3 times my normal force that I just found was 80, is equal to my mass of 10 kilograms times my acceleration. So go through this and find that my acceleration is just 1.1 meters per second squared. So this one's actually a little easier because we don't need to solve a system of equations. All right, so now we get a break from the math and let's just think for a minute. So do I, if I have a little sister who wants to ride on a sled, push her on the sled or pull her from the sled? Well, let's take a quick look at what happens when I'm pushing versus pulling. So in A, I have a free body diagram that would look like, all right, here is the weight of my sister. We'll just say weight. And there's a normal force acting upward. And then I have a pushing force that is F. And so this is at some angle theta. And then I have a friction force that is acting reverse of that. So, writing our sum of force equations for this, I would have the sum of forces in the x is equal to F cosine theta minus little f is equal to max. And in the y direction, I have normal force minus F sine theta minus W is equal to MAY, which MAY is 0. I'm not going to be pushing her through the ground, hopefully. So what's happening here? Well, my normal force in this case is actually F sine theta plus W. So that's going to actually make my friction force, which depends on normal force, larger. That's not very good. To see why that matters, let's look at a free body for the other situation. So I still have the weight going down, I have a normal force upward, I have a friction force resisting motion, and now my force is upward and to the right at an angle of theta. So my sum of force equation here is going to still be F cosine theta minus F is equal to my mass times acceleration in the x direction. But in the y, now I have normal force plus F sine theta minus weight is equal to, it's going to be 0 again. And so my normal force is actually weight minus F sine theta. So what we're doing now is we're proving that when I'm pulling upward, I'm actually reducing friction, because by pulling upward, I am reducing the normal force, which is basically an indicator of how tightly or how much force is pushing together my two surfaces. So, would I rather push her or pull her? Well, I definitely think I would like less friction, so let's pull her instead. All right, so now we have a big system of masses. So we have A and B. So let's go ahead and draw free body diagrams for each of these. So for A, I have mg acting downward. I have a normal force acting upward, so I'm going to call this normal A. And actually, I'm going to go back and I'm going to say that this is not mg. We're going to say that this is mg equal to 50 newtons. Then I have a tension acting to the right. And then I have a frictional force acting to the left. Okay, so this is my A block. Then for B, separate here, I have, I'm actually going to use a different color. Here I have mg acting downward. In this case, my mg is actually 20 newtons. And then I have a tension acting upward. And so these are the same tension because the mass and the pulley, or the cord and the pulley are massless. So tension here is equal to tension there. And the other bit that's interesting is I need this to be my direction of acceleration, which is positive, and then I need this to be my direction of acceleration, which is positive. So from here, we need to set up our sum of force equations. So let's go ahead and set up our blue first, because those are easier. And so what we have is the sum of forces in the y direction, so with down being positive, is going to be 20 minus the tension equals mass times my acceleration. I'm just going to call it A because this is my direction that's positive. So this is nice. I'm actually going to go ahead and solve this for tension. So I have 20 minus, and I'm actually going to go replace the m with 2 because this is mass B. So I got to be careful of that. So I have tension is 20 minus 2a. Now, going back to purple, in the x direction, I am actually going to write tension minus force of friction, which I know is going to be mu k times normal a, is equal to mass A times acceleration. So I don't necessarily know tension yet, but I do know that I'm going to need my normal force. So I'm going to go ahead and write the sum of forces in the y direction. So in the y direction, I have normal A minus 50 is equal to ma in the y. And in the y direction, I am not accelerating. Pretty sure about that. So this actually helps me because my normal force is just equal then to 50 newtons. So let's take this equation and let's do some substitution. So I have, instead of tension, I have 20 minus 2a. So 20 minus 2a. And then I have minus my coefficient of friction, which is 0.2 times the normal force of 50 newtons. And that is equal to mass of A, which is 5, mass of A, which is 5 times A. Okay, so let's clean this up. This is a little ugly looking. So we have 20 minus 0.2 times 50, which is just 10. So that's 10 minus 2a equals 5a. So this is equivalent to saying 10 is equal to 7a, or a is equal to 10/7, which is 1.4 meters per second squared. And that's that whole problem. So we have one more example left. So here I have a skier who's going down a hill. And the force diagram looks something like this. We can redraw it real quick as a free body. So I have mg acting downward. I have a normal force up and to the right. And I have a friction force that is up and to the left. So this is a right angle, but I'm going to go ahead and specify that this is going to be 30 degrees because this is the angle of my incline. So in order to make this easier, I am actually going to take my x and y coordinates and I'm going to kind of do this. I'm going to say, all right, this direction here, let me do that a little better. This direction here where my friction is my x direction. And in fact, because I'm going down the slope, I'm going to call this my positive x down the slope. And this direction with my normal force is my y direction. So how does that help? Well, I know because of how geometry works that this angle must be 30 degrees. And if I redraw this really quick, you may be able to see that a little better. So now I'm going to align friction force going to the left, normal force straight up, and because I moved this friction force down 30 degrees, I know that I need to rotate my mg vector also 30 degrees. So this is going to be 30 degrees away from the vertical. So what we have now is an easier way to go ahead and write our sum of force equations. So I will remind you that I am accelerating down the slope, so my acceleration is this way. So according to my free bodies here, we have in the x direction, we have mg times the sine of 30 degrees minus the force of friction is equal to ma, and this is the x direction. Then in the y, I have normal force minus mg cosine 30 degrees is equal to ma in the y direction. Now, I'm not accelerating into or away from the incline, so this acceleration is 0, which is nice and helpful because my normal force then is just mg cosine 30. So let's just get a number for this. So my skier, oh, I can't get a number because I don't have m. Uh-oh. Well, gee, I guess we just need to plug it in up here. So my friction force, which we say is mu times normal, is now going to be replaced with, so we have mg sine of 30 degrees minus mu times, well, my normal force is mg cosine, mg cosine of 30 degrees, and that's equal to m times my acceleration. Oh, so I see now that actually every single term has an m in it, so I can actually eliminate all of the masses. That's nice and useful. So what does that leave us? Well, let me go over here. So now I have g sine of 30 degrees minus mu g cosine of 30 degrees is equal to a. So I plug this into my calculator using g as either 9.8 or 10, and I find my acceleration is 4.0, and I'm actually going to write this out just a little bit. So I have 10 sine of 30 minus my 0.1 times 10 cosine of 30 is equal to a. So a is equal to 4 meters per second squared. So not too terrible, but rotating axes really, really helps.